Greetings, Science Maximites. Today we're using fizzy drinks in our experiments. And a fizzy drink is just water with bubbles of carbon dioxide gas dissolved in it. So I thought since we exhale carbon dioxide, I could make a fizzy drink by just blowing bubbles in this water. Doesn't seem to be working though, does it? I don't see any bubbles, do you? No. Water does absorb carbon dioxide gas, but I don't have a fizzy drink. Weird. Time to check the book of science. Oh, in order to make bubbles, you have to have pressure. So... this is an air compressor. It takes air and compresses it, puts it under pressure. So... the container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola. 100% science, 0 calories. And your favorite candy, like these Science Experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission because it can get kind of messy. Whoa! What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well, if you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. All right, I just need an expert to help me max this out. Let's see, oh, Cynthia from the Ontario Science Centre. She'd be perfect for this. All right, good. Okay, come on, let's go. And, yep, that's good. Oh, hey, Cynthia.
Hey, Phil.
Cynthia from the Ontario Science Centre, you're gonna help me max out the Science Experiments and Diet Science Cola experiment. Yeah. I think we need a better name for this.
Okay, well, we have the mints that have tiny little pores called nucleation sites on them. The gas inside the cola is gonna go through these nucleation sites, create a giant fountain. So why don't we call it a nucleation fountain?
Ooh, nucleation fountain, I like that. It's accurate and it sounds awesome.
There we go.
Okay, so we wanna max it out. So how many should we put in?
Let's say 5 more nucleation sites.
More reaction. Ah. I tried adding more mints, but one at a time didn't work. It doesn't.
No.
It's not. The bubbles are pushing it back out again. There we go. There we go. And then, yeah, I think if we put them all in at the same time, it would work better. So we came up with a delivery mechanism to get all the mints in at the same time. A tube with a magnet holding the mints up, which we screw onto the top of the bottle. Pull the outside magnet to release, and... Oh, nice.
Oh, yeah.
Oh, yeah.
That's a good fountain.
That is
a good nucleation fountain.
Nucleation fountain worked very well.
There we go.
Cynthia and I decided to try some other ideas to max it out even more. We decided to do some...
Experimentation.
Experimentation.
Oh, that's a good one. Yep.
And see if Diet Cola was the best carbonated drink to use. We tried 4 different kinds: Diet Cola, regular cola, lemon lime soda, and club soda.
Really just
It's just carbonated water.
carbonated water.
3, 2, 1, go. Whoa.
Science cola!
Science Cola, but I think that it was close.
I think it was the release.
Let's watch the replay.
Okay.
Yep, Diet Science Cola went the highest. So the next step is...
Maybe if we want to max the size of the fountain, we have to make a narrower stream.
Ooh, so a smaller aperture opening will be higher pressure
That's what I'm thinking.
because it'll be forced at a smaller opening. What else can we do?
We can launch it.
We could launch, oh, you mean like sideways?
Yeah.
Yeah, I love that idea. So we'll put it on wheels. We'll put it on wheels.
Okay.
And then we'll launch it sideways.
Okay.
We got a lot of things to do. Okay, let's get...
We need time. Let's do it.
Get to it. Okay, we'll go
Okay.
to the lab. I'll get a mop. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up. You take a bottle of tap water, attach it, and carbonate it. Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk. It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice, carbonated hot sauce. No, wait, carbonated, that was the hot sauce. No. Carbonated clam chowder. Oh, there you go, carbonation, not just for water anymore. It is definitely not for clam chowder. No, that's just a big bowl of no. Never again. Cynthia and I are maxing out a nucleation fountain.
Yes!
Oh, yeah!
That's a good fountain.
We're changing our design a bit to see if a smaller hole in the bottle cap will make for a higher pressure fountain, which will make it more maxed out. We have this large hole. We've got a medium-sized hole.
We have a very small hole
So we're gonna see large, medium, or small, which one is the best.
to max out our fountain.
Exactly. But the problem is that our old delivery mechanism won't work if we keep the cap on. So we needed to come up with a new delivery system. So we drilled holes in the mints and put them underneath the cap on a pipe cleaner. They hang at the top of the bottle until we pull the pipe cleaner, and then they fall in.
All right, are you ready?
Oh, I'm so excited. Which one do you predict will be the best? This will have a larger geyser.
I
These
think
ones
this
be
will
smaller.
look cooler
Yeah.
because it'll be big, but this one?
The smallest hole, I think, will go the highest.
Yeah, ready?
3,
2, 1. Definitely the biggest.
There. Whoa, careful, careful, careful. Whoa.
This one is almost like a spray.
It's not like a mist.
Yeah,
it's a mist of cola. They all kind of worked a little differently. The interesting thing is this one lasts the longest.
Oh.
There we go. So, this was cool, but not the best.
This one's still going.
It's still going.
It's not over yet.
You gotta give it points for still going.
I think this fountain looked the best, though.
This one was pretty good. So, a small aperture, but maybe not the smallest aperture would be the best. So because of the force coming out of here, I think that we could probably do something like putting it on wheels.
And shooting it like a rocket?
Yeah, let's see.
On wheels?
Or like a car.
Oh.
Yeah, we'll make a nucleation fountain car. The Nucleation 1! Boo!
It's our race car.
It's our race car. It's got fancy wheels that spin really well.
And we decided to go with the medium aperture. So it's fairly big, but not too small.
Yeah, all we need to do is unscrew that, put that in there, and then pull it out.
3, 2, 1. Oh, good, good, good. Let it go. Oh, that's not so bad.
Whoa, yeah!
Oh, missed the finish line.
It's past the thing. Turn it around, turn it around.
Do you think we can make it get to the finish line?
It's spinning out.
Oh, wow.
Go, go. Yeah! It worked pretty well, but there's always more ways to max it out. What if we just got like a giant container? Like, because we're using small containers, right? What if we just got a really large container?
You want to carbonate a very large container.
Well, we'd have to figure out some way to, well, come on, let's go figure it out.
Okay, let's do it.
This is an egg. It's been hard-boiled and peeled, so there's no shell on it. This is a flask, and this is hot water. I pour the hot water into the flask, which means the air inside the flask starts to heat up. And when it heats up, it expands, and some escapes through the top of the bottle. I pour the water out, and then I cap the flask with the egg. Now this expanded air is starting to cool again, which means it's lower pressure, which means the higher pressure on the outside of the flask pushes the egg in. Ha-ha! Fun! And then, to get the egg out, I can reverse it. If I blow into the flask, I can increase the pressure inside. Science! And now let's max it out. Max out container! Okay, pour out the water. Oh, careful, careful. And now, I put this water balloon on the top, and we'll just see what happens. The hot, expanded air inside the container is cooling and reducing in pressure, which means the higher pressure outside the container, it's happening, pushes the balloon in. It's happening! Oh. Success! Maxed out! Did you know that we live on the bottom of an ocean of air? It's called the atmosphere. And compared to the Earth, it's really thin. I mean, it's about as thin as this. Huh? Huh? Look at that. Not very thick at all. But it's a good thing the atmosphere is around, and not just for breathing. Though I am a fan of breathing. What do we want? Breathing! When do we want it? All the time. But did you know the atmosphere has different layers? It's true. I will walk you through them. No, I mean, come on, you gotta come with me. I'm walking over to walk you through them. Okay, the troposphere. This is the layer where we are all existing right now, where all of our weather happens. There's a lot of air molecules in this layer. Think of these balloons as air molecules. There's a lot of air in this layer. Yay, air! Next layer, the stratosphere. There's less air molecules in this layer, and it's where jets fly. Next layer, the mesosphere. There's even fewer air molecules in here, and it's where meteors burn up and turn into shooting stars. Fire, 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 fire! The thermosphere. Not many air molecules left up here, and this is where the northern lights, the auroras, happen. Woo! Northern lights. And finally, the exosphere. This is as high as the atmosphere goes. This is where satellites orbit, and if you see any air molecules up here, they're just passing through. Hello. And after that, nothing but the vacuum of space. Ooh, the vacuum of space. Of course, you know it's not that kind of vacuum, right? Right. Vacuum just means no air. There you go. The atmosphere. The only thing separating us from the vacuum of space. Roberta, the space vacuum got broken. I don't know how. Cynthia and I are maxing out the nucleation fountain.
This one is almost like a spray.
It's like a mist.
Yeah,
it's a mist of cola.
Just to experiment, we tried using a giant bottle and pouring the Diet Cola in.
I'm a little concerned about the science.
But it didn't work.
Well, that's not very exciting.
Okay, so that didn't work at all.
No,
This is not a chemical reaction.
it's a physical change.
So it's the carbonation that matters.
Exactly.
When we poured the cola into the bottle, we lost almost all the carbonation.
How are we gonna max it out?
That's the question. So if we can't make a larger container,
More bottles?
we just have more bottles. So we'll just get a
Exactly.
lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something. We'll max out the
I know what we
fountain.
should do. You know, we should do sort of like a cascade and we'll get a lazy Susan or This is a vacuum chamber. It's an airtight container, and I put a hose on it, and the hose is attached to a pump. Now, the pump takes the air out of the chamber, creating a vacuum. So, let's have some fun putting things in a vacuum chamber. Marshmallows in a vacuum chamber.
The marshmallows grow larger,
Whoa!
then shrink much smaller when returned to normal pressure. Why? Well, take a look at what happens with this balloon. The vacuum takes the air and the pressure out of the container, which was pushing against the sides of the balloon. Without that outside pressure, the air molecules inside the balloon can expand. So let's max it out with...
Maxed out marshmallow.
Just like the balloon, the marshmallows expand. But unlike the balloon, the air in the marshmallows escapes. So they shrink when the pressure is added back in.
They're almost the size of regular marshmallows.
It's the air inside a marshmallow that makes it fluffy.
It's not very fluffy.
The same expanding process happens with marshmallow cookies.
The marshmallow has completely deflated and it's all kind of hollow inside.
The frosting on a cake.
More cake! No, no! Oh! Look at this giant birthday cake. I can't wait to eat it. No! No! Why birthday cake?
And even shaving cream.
No! Shaving slime.
Cynthia and I have done a whole bunch of different experiments to find out how to max out the nucleation fountain.
So we'll just get a lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something.
Now we have a bunch of bottles and we're ready to try the maxed out version.
We've got our release mechanism.
With our medium aperture.
Yep, and we're gonna put the mints in all of the bottles and then we're gonna release them in a very coordinated,
Pattern.
rehearsed pattern.
Very rehearsed.
We've rehearsed it a couple times. We'll see how it goes. And we've got this lazy Susan, which will spin around and we'll see how it goes. And 3,
2, 1. 1,
2,
3,
4,
5,
6,
7. Surprise! 1, 2, oh, go, 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 3, 4. We did it!
No! Whoa!
It's raining Diet Science Cola. We maxed it out!
Maxed out! Nucleation fountain. That is as good as it's gonna get.
So let's recap. Our nucleation fountain is all about releasing the carbonation in our Diet Cola faster than normal. This happens because there's lots of tiny bumps on the mints for the carbon dioxide to grab onto and make bubbles.
High fives. There you go. Science Max, experiments at large, nucleation fountain. Excellent job. Now all we need to do is clean it up.
Clean up, and I think I need a shower with water.
Yeah, I think I need at least the towel.
Yeah, but it's supposed to volumize your hair.
Is it good for
I
your
think
hair?
so.
I
Yeah,
hope so.
better than
'cause
honey and things like that.
This This episode is all about chemical reactions.
Nom nom nom, nom nom nom, nom nom nom, delicious.
Reactions to make things fly, to make things glow, to make things pop, and to make things fly.
That worked.
Wait, did I mention the flying? I'm sure I did, but I'm mentioning it again because it's awesome. All on this episode of Science Max, Experiments at Large.
Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. Come on, let's max it out. So first, I need an expert to help me. Lisa from Logix Academy, of course. Logix Academy people have helped me launch all the rockets on Science Max. This is gonna be great. I'm gonna get my helmet first. Okay, let's launch some rockets! Let's go! Whoa, wow, it's really dark in this room. I can't see anything.
Bill?
Lisa?
Bill?
Lisa? What?
Bill?
Where did this come from? I guess the portal's malfunctioning. Hey, Lisa!
Hi!
From Logix Academy, great to have you here.
Great to be here.
Let's put this over there. We are here to max out the chemistry rocket!
Ooh, what is that?
It's just a small plastic container. But when we put an antacid tablet in there and some water,
we get a chemical reaction.
we get a chemical reaction. And so that's what creates the pressure. And then that pops the lid off and we get a little rocket.
Kaboom!
But now we're going to max it out. Get a bigger container and more...
Wait.
What?
How about if we launch a whole bunch of them?
Ooh, so we just get a lot of the small one and we launch them all at the same time.
Exactly.
Okay, great. So we just need a whole bunch of these and a whole bunch of...
And a whole bunch of science antacid.
Yeah, well, that's okay. I get them both in bulk. Come on, let's go put it together. I'm an acid, and I'm a base, and we are enemies. Whoa. Well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons. You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react.
Whoa. That is until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need more. I want more. I want more protons. Here.
Water is a solvent, allowing the chemical reactions to take place.
Depending on the strength of the acids and bases, that reaction can be mild. Would you like a proton?
Oh, no, really, I could.
Please take it.
Oh, well, thank you, that's very generous.
Have another.
No, perhaps, maybe I will.
Here's
Yes,
one.
Okay, maybe just one.
But if the acids and bases are strong, the chemical reaction can be really extreme.
This is what's going on in the antacid tablet, and why, without water, nothing happens.
Oh, water!
Water!
Come
Acid,
on!
what'd you do?
What?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket, not by making it bigger, but by making more of them. How many more? 400 caps all glued down, 400 antacid tablets, or part of,
Yep.
all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down. We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on. Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flip the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah.
Oh my goodness! Ah!
It's good luck if you catch one.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go and we'll clean
All
this
right.
up afterwards.
Yeah,
okay.
let's do it.
Okay, let it go. Whoa. Whoa. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it. That separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go! Our first attempt to max out our chemical rocket was 400 plastic containers. Oh yeah. That worked well, but now it's time to make the container larger. Whoa! Giant maxed out chemistry rocket canister. I have a big plastic container with a groovy lid that sits there on airtight, which is great.
And I have a giant jar of antacid.
How many? It was like 60 antacid tablets or something?
At least.
This works exactly the same as our smaller containers. We dump the antacid in, seal the lid airtight, then flip it over. And now would be a good time to mention not to try this at home. Okay, it's not gonna take long. All right, so that was the canister version. Now we need the pop bottle version, the rocket version.
Yes.
Okay, let's go make that.
Let's do it.
Okay. This is a light stick. It creates light using a chemical reaction. There's a liquid chemical inside and also a glass container that holds another chemical. When you bend the light stick, you break open the container and the two chemicals mix, creating light. There you go, light sticks, chemical reaction. And yes, of course we're gonna max it out. This is a whole bunch of the two chemicals in a light stick. Let's max it out. So how does a chemical reaction produce light? Well, a lot of chemical reactions produce energy. You might think of a chemical reaction producing heat. Well, heat is a kind of energy. This chemical reaction also produces energy, just energy in the form of light. It's just a different kind of energy. Whoa, maxed out light stick! And now for a Science Max quiz. Chemical change or not? What's a chemical change? Well, let's demonstrate. Look at this. It's a happy little molecule of iron. And here's another molecule of oxygen. If they were to have a chemical change, they would react and form different molecules. Look, it's a molecule of rust. Rust is a different chemical than either iron or oxygen. It's a chemical change. Now, if these molecules mixed and did not change, then it's not a chemical change, it's a physical change. Sometimes it's hard to tell if it's a chemical change just by looking, but asking what kind of change it is leads to good science. So let's look at some examples. Vinegar and baking soda. Is it a chemical change? Yes. Vinegar and baking soda react to form different chemicals. Sodium acetate, that's the white stuff that's left over, and carbon dioxide, which makes the bubbles. How about a nucleation fountain with Diet Cola and mints? Haha! A lot of people think that's a chemical change, but it's not. The mints cause carbonation, the bubbles, to escape faster. But in the end, you still have cola and mints, no new chemicals. And without the carbonation, nothing happens. So it's a physical change. Take a guess at this one. Glow stick chemicals. Well, producing light or heat is usually a sign of a chemical change. How about mixing sugar and water to make a sugar pop? That's a physical change. You start with sugar and water, you mix them, and when you have a sugar pop, what chemicals are you left with? Well, sugar and water. So, no chemical change. It can be hard to tell sometimes, but whenever two things mix, think to yourself if it's a chemical change or a physical change. And now you know it's either one or the other. And that's the first step to good science. Thanks for playing our Science Max quiz. Our maxed out rocket worked great. Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right.
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah.
And so the magnet sticks to the paper clip.
And so that's what we have here. You see the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic. So we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher like so. All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go. And then, as we pull the bottle over, we bring the bag up this side,
And there, the water and the antacid have never touched.
No reaction.
All you need to do now is we pull this magnet away and the bag will fall into the water. And then we will have the launcher down here. And we pull the release and the rocket will go. We add some weight to the launcher to help keep it in place. Okay, right, wait, glass in.
Safety first.
Okay, ready? And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
Three, two, one, launch! Woo! That worked.
Yeah, it hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of these. 3, 2, 1, go! There it is. Yeah! We tried it outside and it worked great. The only thing left was to max it out even more. So, larger chamber?
Yep, more antacid.
More antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together and we can increase the size of the chamber. This is sodium acetate. How do you get sodium acetate? Well, when you do a vinegar and baking soda reaction, what you have left once the reaction is finished is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a super saturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform. Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this. Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right before your eyes. Because we heated the water, it allowed more crystals to dissolve in it. Ooh. But then it cooled down afterward. There's more crystals sitting around in this water than there should be at this temperature. They want to turn back into crystals, and all they need is something to start them going. I've colored this one green because, I don't know, science. Maybe it'll look cool. A tiny crystal on the end of the stick is all we need to start the reaction happening. Whoa! Wow! And there you go, sodium acetate. That one wasn't done yet. We've gone from small containers, oh yeah, to a large container, to a rocket. Yeah! So what's next? Super maxed out rocket! 12 2-liter bottles all spliced together to give us a very large chamber to build up pressure with. So the chamber is all the same, so it's all one big hollow tube, and now we're gonna fire it off. Let's go!
Let's do it!
Awesome rocket! Yeah! Lisa and I follow the same procedure as before. We use a bag of antacid tablets held up inside the rocket with a magnet. And once it's sealed on the launcher, we pull it off, let the antacid mix with the water, let the chemical reaction happen for a while to produce enough gas pressure, and then we fire it. Okay, here we go. 3, 2, 1, go!
Oh my God!
That is the highest I think we've ever shot a rocket on Science Max.
That's amazing.
Well done. Chemical reaction rocket. Thank you very much for joining us on Science Max Experiments at Large. We should build another rocket because that one is probably broken.
That's done.
Okay, let's go.
Let's do it.
All right, so this time I think what we should need to do is... Oh no, it's nothing but garbage cans in there. We gotta turn the portal off. Come on, we gotta get...
Today on Science Max, it's all about the power of water. I'll see you later. We filter it, pump it, paint with it, and most importantly, use it to crush stuff.
Oh, crushing!
All on this episode of Science Max, Experiments at Large.
Ha. Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need.
First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store.
Here's how you build your own hydraulically powered arm.
First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together.
Because we are holding this whole thing together with elastics.
Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe.
Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over and that way. Oh, Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat. But this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes.
Yeah, because we got some cool stuff planned. Okay, so we're just gonna get the table in here. Whoa, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We can make it bigger, we can make it
What if we did it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
A I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we can do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small.
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No! My cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale.
See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger.
So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible.
It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much.
So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass.
Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating.
That's impressive. Should we try something else?
Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat.
The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right. Wait, hold on. I will remake the crackers into, see, look, see, it's fine. It's fine. I'm not really gonna eat that. I'm just kidding.
Chris and I are maxing out our hydraulic crusher.
Yes. Before we get to that, I have a little game I want to play.
Okay, great.
Okay. You can pick either the small one.
The big one.
Okay.
So what's the game?
Simple thumb war. I'm gonna press down this side. You press down that side. We'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go. Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go. Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
Let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go.
Ooh, how about an orange? 1, 2, 3.
We squeeze down and... Then we tried a walnut.
Are you allergic to nuts?
I am not.
1, 2, 3.
When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do.
We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we
we can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal.
Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a
gravel, sand, and charcoal filter.
The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water.
Delicious. Science.
Max Historica.
This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw. Which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right. Used to make holes in water.
What? No! Look, did you even do your homework?
Hold on. It's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut.
It's cracking. Oh, there we go. Oh, it's gonna leak.
And then a can of pop.
Science Max Cola, now in the new smaller can.
Let's really challenge this press. Perfect.
A piece of wood.
We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping.
Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern.
Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet.
If you put tape on what you're painting, you can remove it later to make parts that aren't painted.
Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants.
Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad.
Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table.
To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with
A little happy town.
This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle,
Look at the soil, it's all getting eroded over here.
or the way the town is laid out.
Every time you do it, the river goes in a different direction.
And have fun.
Oh, phew, I'm tired. I'm just gonna lie down. And that is the power of water.
Chris and I are maxing out a hydraulic crushing machine.
What about this? Is this what we're gonna use?
We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab.
Oh, this is good. Oh, look at that! Oh, is this what we're using?
No.
Oh, I can use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it. This is it.
Yeah, right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. Okay.
We started out with the piece of wood which defeated our last press.
And go!
That sound.
Awesome. Reversing.
It turned our wood into a pancake.
Whoa, totally flathead.
So it was time to try some other stuff. We crushed a ball of plasticine.
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball.
Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind.
This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press.
This is a metal vise. Hard, strong,
Yeah, it's steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally exploded. Science, Max! Experiments at large, hydraulics. Whoa. Nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse.